In this section, we will talk about inferences. Let me start. Okay. Start with the objectives. We're going to develop hypothesis test and confidence intervals for the slope and intercept for our least square regression model. And we'll include assumptions for the model and check bias of the estimates. Basically, we will prove the estimates. Some of the estimates are unbiased, and we'll also check the variability of the estimates. Well, to follow the example that we were showing about the voting in 2008 and 2012, we put this in English, like for the inference. We are checking, is the percentage of the states that voted for Obama in 2008 linearly related to the percentage in 2012? So this is something we are trying to make inference. Start with assumptions. In order to make the inference, we would have to get some assumptions to get us going. For now, we make the following assumptions, and I use LINE to help you better remember the assumptions. So here, L means linear. So L is for y is related to x by the linear model. This yi equal to beta 0 plus beta 1 xi plus ei. So L for linear. I is for independent. And the errors are independent of each other. So this EIs, they are independent for different I. And for normally distributed. The errors are normally distributed with mean 0 and variance of sigma square. And put it in the stat format, this error, once x is given, would follow normal distribution, mean 0, variance sigma square. E stands for equal. The errors have an equal variance. This error E, they all have the same variance, sigma squared. So each of this EI will have variance being sigma squared. So LINE, line for the 4 assumptions to make inference for our linear model. And in the inferences, we will discuss different assessment for the simple linear regression model. Means hypothesis testing of whether there is a relationship between x and y, and finding a confidence interval for the size of that relationship, which is basically for the slope of the linear relationship, and also finding a confidence interval for the regression line. So that's for the whole line. Predicting a new data point y star for a specific value of x star with the linear relationship we fitted. In the end, we will assess the accuracy of the model with 2 different methods. Okay, some notes on the variance of the residuals. So again, our model is this linear model, yi equals beta 0 plus beta 1 times xi plus ei, and I goes from 1 to n, where this random error ei is normally distributed with mean 0 and variance sigma square. And this sigma square is the population parameter, which we do not know. We want to estimate this variance term, sigma, by the sample variance, where we basically replace the coefficients with their least squares estimates and show that this sample variance is an unbiased estimate for sigma square. So write it out. This S squared is our residual sum square. Remember this RSS is residual sum squares divided by n minus 2. Well, this is hopefully this is familiar to you, like the sample covariance, sample variance. Normally we would have this RSS divided by n minus 1, but in this case we have n minus 2. Why? Because we have estimated 2 parameters with the data you have, so so you can understand it as we lost 2 degrees of freedom by doing that. So this this divisor would be n minus 2. And mathematically, to understand it, we just want this S squared to be an unbiased estimator for sigma square. So when we take the expectation of this S2, it needs to be equal to sigma square. If you use n minus 1, then they are not equal. So it's not no longer an unbiased estimator. So that's another reason for understanding. That's another reason why this is n minus 2, not n minus 1. Just like you might have wondered why it was n minus 1 instead of n when we do a sample variance, like when you first learn in the fundamental statistical class. So here, similar reason, but the quantity changed from n minus 1 to n minus 2. Okay, so this is our estimate for sigma square. Okay, next we will check if this slope, estimated slope, estimated parameter beta hat. So notice that this beta hat is a vector, which include both the slope and intercept. And here I'm showing you this, our least square estimates are unbiased estimates, which means when we take the expectation of this beta hat given x, we will get the population parameter. So that means they are unbiased. Let's go through this line by line. Remember this beta hat, when we have our matrix format, we get beta hat given x equal to x prime x inverse times x prime y. This is something you're supposed to know, to remember. So when we take the expectation, because x is given here, so it is fixed. It's no longer a random quantity. In this in this term, only this y is a random quantity. So this expectation would go to y. So you say here, and we use x beta plus e to replace this y. It will be like this. And again, this x is given and beta is a population parameter, which is fixed. So this expectation just go to this random quantity error, this e. And remember the, what we said about this error. So the random error EI is normally distributed with mean 0 and variance sigma square. So mean 0, which means this expectation is just 0. So it's gone. That's why you get only this x beta. So, and this inverse of x prime x will cancel with this x prime x. So eventually we get the population parameter beta. So this is how we know this beta hat, our least square estimates, they are unbiased. So it's proved, right? And also we will need this when we do the inference in the following steps. Okay, what about the variance of the estimates? So here we got the mean, the expectation of the estimates. Now we care about the variance of the estimates. So again, this beta hat given x is still in this format. This is classic thing you need to know. And when you take the variance, do you still remember when we do the basic, when we go through the basic matrix calculus, we learned how to take the variance of a vector multiplication, like the variance of a prime y, or I forgot it's ay or a prime y. But we have that formula there. Just go check it out and apply that little formula here. You will see this, like this quantity in front of this y will go first, and then on the right hand side, after this, the variance of y, that is the transpose of this quantity, right? This is this part. And again, we write this y odd being x beta plus error plus e. And only this error e is a random quantity. So we have its variance right odds, which is we use sigma to represent the variance of error. Well, what is the sigma? We said the errors have independent, they're independent, and they all have equal variance being sigma square. So if we write it in a matrix format, it will be a diagonal matrix with all the identity matrix. I'm sorry, diagonal matrix with all the diagonals being sigma square. So write it out here. It's just sigma square times this identity matrix, right? This sigma square is just a scalar. We just put it in front, and this I just goes. It just disappear after you multiply with any matrix. So you get this, and then this and this canceled. Eventually, you get this sigma squared times x prime x, take the inverse of x prime x. So this is the variance of the least square estimates. Well, why we get this mean and this variance? Because we need it in this page. You will see. So again, the equation of the slope, I just read this out just to remind you that it's a linear combination of normal random variables, this beta. Normal random variables, I mean this x is given, then this y is normally distributed. Being a linear combination of those, beta 1 hat is still normally distributed. Given x, I said x is given, y is normally distributed, beta 1 hat is normally distributed. So we just need its mean and its variance, then we know its distribution, right? And we already got it from the previous two slides. As shown that this is unbiased estimate, so the expectation of this beta 1 hat given x is just beta 1. We actually showed both the intercept and slope, they are unbiased estimates. Here we just focus on this slope, so its expectation is just equal to the parameter beta 1. And we find that the variance of beta, beta 1, the slope here, beta 1 hat, given x, is the sigma squared divided by xx. So this xx is nothing but calculus format. the mathematical format of this x prime, x we had on previous slides. Okay, now we know the whole distribution of the estimate of the slope. So beta 1 hat given x following normal distribution with mean beta 1 and variance sigma squared divided by sxx. Well, knowing the distribution of our estimates will give us the ability to do statistical testing. So that's the whole purpose why we have to find out the detailed distribution for our slope. So if we standardize the distribution, we will get, well, standardization means we take this beta 1 hat minus its mean and divided by its standard error, which is the square root of the variance here, right? We get standard normal distribution. So this is normal 0, 1. And if sigma is unknown, which we know in our case, sigma is unknown, we replace it with this, sample standard deviation. So previously we get the S squared, the sample variance. Now we use this S to replace this sigma. And we get a t distribution, right? Hopefully you still remember. This is something you're supposed to know. You learned from a basic statistical course, where when the sigma is unknown, you use this sample standard deviation, replace the sigma, and it becomes a t distribution. And yeah, so I write it here. This is beta 1 hat minus beta 1 divided by its standard error. And this follows a t distribution with degree freedom n minus 2. So again, this n minus 2, this 2 comes from, we lost 2 degree freedom when we estimate this betas from our linear model. Okay, now we can do a hypothesis testing on the slope. So the hypothesis we have, the null hypothesis being beta 1 equal to some fixed value, if we call it beta 1, 0. And the test, the statistical we have here is this t being beta 1 hat minus beta 1 divided by its standard error. And we know it's a t distribution with degree freedom of n minus 2. This t value is actually reported in R, and the p value is the one, the p value in the R output is associated with a two-sided test, where the alternative testing is beta 1 not equal to 0, and beta 1, the null hypothesis is beta 1 equal to 0. So we have run this election example and got our R output, where you see this, this is the p-value associated with this testing. Additionally, we can get our standard error of the estimated slope. So this line is for the estimated slope. So this is the estimated slope, and this is the standard error of it. So it's that easy. You do not need to really look up the table and do the calculation by hand. You'll just get everything from this R output. Does that sound good?